Good evening, everyone. Uh, Welcome to the class on electrochemical impedance spectroscopy. My name is Sri Lakshmi. I'm doing the TA for this course, electrochemical impedance spectroscopy. I'm a second year PhD scholar in the Department of Chemical Engineering at IIT Madras. And you all are aware that this is a 12-week course. So every Tuesday from 7 p.m. to 9 p.m. we'll be having the regular class where I'll be summarizing what has been taught for 1 week, and I'll also be discussing few of the questions related to what is taught. So I hope that this discussion will help you to clarify your doubts and also help you in solving the assignment. So if anyone has any doubts regarding what was taught in the previous week, you can ask me. And if I'm aware of that, I will clarify or I'll get back to you soon with answers. So without any further delay, we'll start today's class. Um, I hope I'm audible to everyone. If someone, okay, fine, thanks. So yeah, so we'll start today's class, and so this is the first tutorial for the electrochemical impedance spectroscopy. So we'll start with the summary of what was taught in the last week. I'll take few minutes to explain on what was taught last week. So this will just help you to refresh your memory, and that will help us in solving the questions better. So the first thing that was taught was the electrode-electrolyte interface. So in which we saw that when an electrode is immersed in an electrolyte, what happens is on the surface of this electrolyte. So this is the electrode which is immersed in an electrolyte, and at this interface of electrode-electrolyte, you will see a charge separation. So basically, uh, so basically the metals will gain some charge at the interface. So for example, if I say it is positive, so what happens is similarly from the source, so this is the electrolyte. So at that interface, what happens is the,
Excuse me, ma'am.
yes, tell
We
me.
can't see your slides, ma'am.
Okay, okay, I'm sorry. Yeah, I forgot to share, I think, I'm sorry. Is it visible now?
Yes, ma'am.
Okay, thanks. Please interrupt me in case you face any difficulty with the slides, so I'll be aware of that. Thank you. Yeah, so we'll start today's class. So the first we'll go through the summary of what was taught in the last class. So yeah, so if an electrode is immersed in an electrolyte, I'm just showing what will happen in the electrode-electrolyte interface. This is the electrode, and it is immersed in an electrolyte. At the interface, you can see what will happen is there will be some kind of charge that will be charge separation happening within the electrode. So say for example, it can be positive or negative. So say for example, there is a positive charge that is coming on the electrode surface. Similarly, from the electrolyte, the entire electrolyte, from the bulk electrolyte, it will be the negative charges which will be coming on the surface of the it will be getting attracted towards the surface of the metal. Now simultaneously what happens is another layer of charge separation will also occur inside the electrolyte. So if it was negative in the inner side, means at the outer side it will be positive. So you can see that there is a double charge separation that is happening. So this forms the inner Helmholtz layer or IHP. Okay, and you have the inner Helmholtz plane, and this one is the outer Helmholtz plane. So this is the Helmholtz model for the charge separation, the electrode electrolyte interface. So though I am drawing it very big, you can see it will be in a narrow region. So this will be as small as 1 nanometer. So such a charge separation is happening only at a small region of 1 nanometer. So this is what is the first model that we saw in the electrode electrolyte interface. Now this is the first one. Now the next one that you guys saw was the Gui-Chapman model. So what is Gui-Chapman model saying? So Gui-Chapman model says that this kind of charge separation. So here you see that 1 nanometer range. So according to Gui-Chapman model, this charge separation is not happening in a small region. Instead, it is little more distributed to as high as 10 nanometer. So this is what is Gui-Chapman model saying, that is, you'll see a charge separation which is happening around a larger region. So that is as 10 nanometer. Now the third model that you learned was a combination of the Gui-Chapman model and the Helmholtz model. So basically what it says is most of the charge will be distributed over a most of the charge distribution will be happening around this 1 nanometer region, whereas the rest of the charges the rest of the charges will be seen in the 10 nanometer region. So basically it is not at 1 nanometer or across the 10 nanometer. It is basically you have most of the charge separation happening across the 1 nanometer, and but some will also be extended towards the 10 nanometer. So that are the three models that you saw in the electrode-electrolyte interface. So then we saw that because there is a charge separation happening positive and negative together, we saw that this can be represented using a double capacitor. So this double layer formation is represented using a capacitor. So that was the next thing you had seen. Then after that, you came across the electrochemical reaction. So what is an electrochemical reaction? So electrochemical reaction is nothing but along with the chemical reaction, there will also be a electron transfer happening. So that is what. So electron transfer along with the chemical reaction, you can say that that is the electrochemical reaction. So this was what was covered in the electrode-electrolyte interface. Now the next thing you learned was the reference electrode. So if you want to measure the potential of a single electrode, if you want to measure a potential of a single electrode which is immersed in an electrolyte, what was told is you cannot measure that alone. Instead, how do you measure the potential of an electrode? You need a voltmeter. So we know that voltmeter will have two ends. So one probe will be connected to the electrode whose potential has to be measured. The next electrode will be immersed directly into the solution. But what happens in that case? There will be a potential drop also across the second probe. So basically you cannot measure the potential of a single electrode. What you are actually measuring is a potential of an electrode with respect to another probe if you are using a multimeter or a voltmeter. So you cannot actually measure the potential of an electrode on its own or a single of a single electrode. So what can you do in that case? So what you can do is you have to measure this potential of this electrode in different electrolyte. So how exactly we can see that potential? So what we can do is we can take something known as a reference electrode which will have same drop of potential across any solution. So basically whatever you will be measuring will be the potential of one particular electrode, because the reference electrode is having the same potential drop in every solution. So that is the need for using a reference electrode. So in order to have so basically reference electrode is something that will help you to which is having a constant potential drop, and that will in a way help you to measure the potential across that electrode. Now the third topic that you learned was the counter electrode. So what is counter electrode doing? So counter electrode is when you're passing large current through the working electrode, what happens is this current is passing through the reference electrode to complete the circuit. So when you're connecting the two electrodes together, what current passes through one should also pass through the other. But what happens? Reference electrode is something that should have a fixed potential in every solution. So when you're passing a large current through it, what happens is you are actually altering the performance of the reference electrode. In fact, it cannot maintain a constant potential across that particular reference electrode. So what can we do? We can pass this current we are passing through a working electrode through another electrode known as a counter electrode. So counter electrode is used to take away that current that you are passing through the working electrode. In there you also saw that this counter electrode should have a large area because when the area if you are passing some current if you are applying some potential across your working electrode, what happens is a current is generated. So if you are applying a larger potential, the current will also significantly increase. So whatever current is passing through the working electrode will be passing through the counter electrode. So in case what happens is, if the area of the counter electrode is very small, the current per unit area, so if the area is small, current per unit area of that particular counter electrode will be large. So that is not good. So basically what you can do is, we can give a large area so that the current per unit area of the counter electrode will reduce. Okay, so that is needed for the better performance of the potentiostat or the tester. So when the potential you are applying across the working electrode is actually supplied by your interest, but that potential which you are applying, based on that a current will be developed. The same current will be also going through the counter electrode. So in order to maintain that particular current at the counter electrode, it will be the machine or the equipment potentiostat that will be applying that particular voltage at the counter electrode side. So if the current through the counter electrode increases, that voltage will increase, and that is not good for the equipment. So if the area is large, the current per unit area will be reducing, and the potentiostat will have to apply a lower potential in order to maintain that current. So basically, in order for the better performance of the equipment, we can have a large counter electrode area. Now the next thing we had learned is the supporting electrolyte. So what was told in supporting electrolyte is, sometimes the solution might not be that good conducting. So what happens is, you will not be able to perform the experiment because the electrolyte will not be conducting the ions properly. So in order to increase the conductivity of the electrolyte, we can use something called as supporting electrolyte. So basically what it does is, it increases the conductivity, but it does not change the quality of the electrolyte, or it is not interfering in the reaction. So it is only to improve the conductivity we are using the supporting electrolyte. So then the next thing we learned was, the fifth one we learned was the resistor, capacitor and inductor. So we learned that EIS, or the next part we're coming to is impedance. So basically what we are actually supplying is a DC voltage. We have a DC voltage which is superimposed by a small small amplitude of AC potential. So in order to measure the AC voltage, the resistor will only allow the DC source to pass through. So what exactly allows the AC to pass through is capacitor and inductor. So whatever we get the impedance, we are representing it in a combination of resistor, capacitor and inductor. So we then learned in that so how the current is, how the potential is, how are they in phase or are they out of phase, and which is leading what. Then we learned how to find out the impedance of these resistor, capacitor, inductor. So in combination of those, we will be representing the impedance of that particular system. So that was the next topic we learned. Then after that we learned admittance. Admittance is another form of impedance, which is nothing but, admittance is represented by A, and it is nothing but, it is the inverse of impedance. Okay, so impedance is represented by Z and admittance is represented by A. So admittance is nothing but, it is the inverse of impedance. So this is what we even you're solving problems, you can either use admittance form to solve the problem, or you can use the impedance form and you can solve the problem. So that was the next thing. So the next thing we learned was a series parallel connection. So in series parallel connection, so basically to represent the system, I told that we can use a combination of resistor, we can use resistors, or we can use capacitors and inductors in combination. Again, one should keep in mind we cannot use anything as such. Everything will have its own significance, or using this and this in combination in something, or like each one has its own significance, which will be taught to you in the later stages of this course. So how to find out the impedance when we are, so that is represented in a combination of all this in series or parallel. So how can we solve it to find out the impedance of the system? So that will be studied here. So basically, you know that the impedance will have it will have a real part and also an imaginary part. So, and this is one way of representing, that is in the form of A plus IB format you can represent, or you can also represent it in polar form where it will have a magnitude and a phase. So both the ways are acceptable. So it is based on the convenience that we use each one to represent. So these topics will be covered in the graphical representation. So when we are applying frequency, we'll get an impedance which will be a combination of real and imaginary, which can be either represented in this form or this form. So based on that, we can either call it as, so as you all know, there are different ways of representation. It can be either Nyquist plot or complex plane plot, or it can be a body plot. So this was learned in the graphical representation. And finally, you also learned about some electrochemical technique. So that is left out here. So the electrochemical techniques that you learned was OCP. So what was OCP? When you are applying zero current, when no current is passing through it, what is the potential? What is the potential the system can give? So that is what is known as the OCP. So basically, when an electrode is immersed in an electrolyte, you know a double layer is formed. So with time, when the double layer is forming, this potential that is measured at zero current keeps changing. So unless or until a stable electrode-electrolyte interface is formed, this value keeps on changing, and once you get a stable interface, this potential value is becoming a stable one. Then after that, you learned PDP. So PDP is something where you're applying a potential, or usually over the range of plus or minus 250 millivolt, and this is usually done at a slow scan rate of 0.1 millivolt per second, or maximum 1 millivolt per second. So you scan it at this rate from minus 250 millivolt to from plus 250 millivolt to minus 250 millivolt. So going positive with respect to potential, that means you are going to a cathodic region. So basically, you start from a cathodic region and you sweep through and you come to an anodic region. So this usually this is a slow scan region. So and this usually done with stirring. So stirring is done so that any product that is formed can mix with the solution, and there is a uniform concentration maintained, and you do it at a slow scan. So basically, when you do it at a slow scan, you're giving more importance to the reaction happening, and you can neglect the interface formation. The impedance due to the interface. Then the next one you did is cyclic voltammetry. The thing is similar to PDP, the only difference is scan rate is high. So scan rate is as high as 10 to 50 millivolt per second. The scan rate is very high, and here you're not doing any stirring. So basically, you can see a product build up near the interface. So that is the difference between the CV and PDP. So both of them will give you a same what to say, when you're applying potential, you try to find out how the current is varying. And then you also learned on the last one you learned was quartz crystal microscope. So quartz crystal microscope will also help us to understand if there is a mass deposition or mass depositing on the electrode surface, or something is getting out of the electrode surface. So any mass change during the reaction can be understood by this technique. During the So when a reaction is happening, how is the mass changing at the electrode surface can be understood, and also the charge. Also, the charge change in charge can also be studied during the QCM method. So these are the topics that was covered in the first week. So I hope this clear to you. So now based on this, we'll clear few problems uh, related to this topic. So I would discuss one problem. So basically it will be like I'll be discussing a problem. I'll give 2 or 3 minutes to everyone to solve, and so it's not only numerical, it's also some are theory based, so you can actually flip your pages and find the answer. If anyone finds, they can either unmute and answer, or you can put it in the chat box, that's okay. Then we can discuss about that topic. So that's how I plan to do uh, the tutorial session. So I hope that is clear to you. So let's move on to the first question. So this is the first question. How do we represent a two electrode setup in EIS? So I can give you 3 minutes. Please try it out. And if anyone has any answer, please feel free. Yes, please tell me. Yeah,
Option C, ma'am.
option C. Okay. Someone has raised the hand. Could you please tell me what your query is? Parminder?
Yeah, it's option C.
Yeah, it is option C.
Option C.
Okay, good. So
So
two
it's a
people.
ohmic and concentration polarization.
Yes. So for anyone who is not aware of this, I'll just explain. I understand that a few people have understood the answer already, but for everyone, I think I'll just go through once again. So, as I mentioned, when an electrode is immersed in an electrolyte, it is forming a double layer at the electrode-electrolyte interface. So, basically, that because there is a charge separation, one positive, one negative, or something like that, you can represent it using a capacitor. So capacitor is used to represent the scenario when it is just a double layer. That is, there is no reaction that is happening. Okay. Now you can consider a case when some kind of chemical reaction is happening at the electrode-electrolyte interface. So what happens is you have to take into account the reaction. So for a particular electrode, you will have a double layer and also a reaction. So reaction is represented by Faradic impedance. So whenever a reaction is happening, you apply a potential. There is a current that is developed and that is flowing. So what happens? That will offer a resistance. So that resistance is known as the Faradic impedance, or a resistance due to an electrochemical reaction. So this is the representation of a single cell, single electrode. So you know that for you need a two electrodes to form a setup. You cannot measure a potential of one single electrode. So what happens? You have one electrode and another electrode. So similar to this, there will be the other electrode also, which is having a capacitor and the Faradic reaction happening at its interface. So that I am representing again by setup. So now what happens? So both are immersed in an electrolyte. Okay, so both are immersed in an electrolyte. What happens is the solution itself can offer a resistance to the flow of current, right? So because of that, that is solution resistance. Because the solution is offering a resistance, we can represent it as this. So this is nothing but solution resistance, which I say as RSOL. Okay, so this is for one electrode, this is for the next electrode, and between that you have the solution resistance. Now my question is, now imagine I am asking you another question based on this topic. How will you represent a two electrode setup if in case one of the electrode is a reference electrode? Can anyone tell me? So what I mean is, instead of two electrodes, that is, you are having X and Y electrode, of which I am telling you Y electrode is a reference electrode. So how do you think is the EIS, the representation going to be? Can anyone tell me?
Option B then.
Option B. Anyone else? Anyone else?
I think one single resistance and the single RC.
Single resistance and single RC. Okay. Someone else? Anyone? Okay. So it is actually a combination of what both of you have told. So why? I'll explain. So as mentioned, you have an electrode. Okay. You have an electrode and your another electrode is reference. So the first electrode will be having, as I mentioned, there will be a double layer formation, and for any electrode you take, irrespective of anything it is, whenever an electrode is immersed in a solution, it will form a double layer at the interface. So and it will also have an impedance in case if a reaction is happening. So this is going to be the what to say, the impedance representation for a single electrode. Okay, now, so irrespective of what the condition is, so this, any electrode system, when you are doing the impedance, the representing it, you have an electrode immersed in electrolyte and it is told some reaction is happening. This is the representation. If it is told no reaction is happening in specific, then you can use this one. That means this one won't be there. This one or this one. So this is the first one. Now, so this one or this one. So this happens when you have a reaction. This is happening when it's not having a reaction. So this is the first part. Now, what did I tell you? There is a reference electrode. What is the property of a reference electrode? It was mentioned in the class that in the week 1 lectures that the function of the reference electrode is to maintain a constant potential across the its electrode-electrolyte interface, so that whenever you measure the potential of any particular electrode in any solution, it will have a constant potential drop. So what changes actually will be the potential drop across the this particular electrode, not the reference electrode. So in such a case, what should happen? It should offer a minimum resistance for the current to flow through it. So so that its potential, so it is having a constant potential and should not offer much resistance. So in such a case, we usually neglect this part. So this is for two electrodes. So I'm saying that one of this is reference electrode. This part will not be there. Okay, the reference electrode's impedance will not be shown, so it is not having a reference. But what happens? You have an electrode and you have a reference electrode. Both are immersed in a solution. So when there is some charge transfer happening, ion transfer happening across the solution, there will be some resistance. Solution will offer some resistance. So that impedance needs to be shown. So that impedance is this one. So if one of your electrode is reference electrode, this is how the system will be. Okay, so someone told me can be a capacitor with resistance in parallel. If in specific it is told that no reaction is happening across the surface of the electrode, then you can use this one instead of this one. So basically this one is for any electrode represented by a double layer with a reaction, and you will have, when it's immersed in a solution, you will have a solution resistance, and one more electrode, you will have either this one, or if it is a reference electrode, you will have nothing. So this is how you are representing the EIS for of system. I hope this is clear to everyone. If anyone has a doubt, you can please interrupt me, so or else I'll move on to the next question. Okay.
So for three electrodes, if we include the counter electrode, then how we have to represent?
It will be again in series.
Okay, okay, understood.
And so basically it is also dependent on the reaction that is happening. So basically for a simple two electrode system, this is the significance. So whatever plot you get, so I hope you all are aware that this system as such, I mean, this is just the representation. You can actually plot this in MATLAB. So you'll get the curves. So from the curve, again, you can get some ideas. So any curve you get, it has its own significance. You cannot simply say that if I have one electrode, another electrode, you cannot directly put some symbols and say this is how you represent. No, everything has its own significance. That was what I was saying. So here itself, one capacitor, that means it is a double layer formation on the electrode-electrolyte. And if some reaction is happening, you can show it in parallel to it. So sometimes if it is parallel, so this ZF, that is the simplest way of representation. What is a ZF? ZF can be a single resistor, it can be many resistors in parallel, or it can be something else. It can be a combination of resistor and capacitor. So that ZF varies. So that representation of ZF depends upon the chemical reaction. The simplest way of representing the overall two electrode system is what is shown over here. So please understand, whenever you are assigning any value, any symbol, it has its own significance. Please understand that and then assign something. So only then your the impedance analysis is making a sense, or it is having a meaning. So that is the sole purpose of this course also. Okay. So if anyone else has any doubt, if not, I'll move on to the next question. Yeah. So which model can be used to describe the charge distribution in an electrode-electrolyte interface in a solution of 1 millimolar concentration?
C.
Okay. Anyone else?
C.
C. Okay.
Option A, ma'am.
Option A. Okay.
Option A.
Okay. Anyone else wants to answer? Okay. So the correct answer is option A. Okay. So now I'll tell you why. So we learned three models. So the first one was the Helmholtz model. So what it says is you have an electrode which is immersed in an electrolyte, and you will have a charge separations happening. So according to Helmholtz, this charge separation, so there will be in a layer of positive charge or negative charge. Accordingly, there will be an outer layer. So corresponding to what is forming an inner layer, its corresponding opposite polarity one will be there in the outer layer. So this one is happening over a small range. Okay, in the small range of 1 nanometer. Okay, and here, according to Gui-Chapman model, this is happening at a larger region of 10 nanometer. Okay, it can be more than 1 nanometer. We say it is the Gui-Chapman. So, and here it is a combination. Most of the charge distribution is happening in the 1 nanometer region and some towards the outer region. So the electrolyte is having the ions, right? So if it has to form a double layer, what it has to do? These ions must come from the solution and it should get absorbed onto the electrode surface, right? So the ions are coming from the electrolyte and it is forming a double layer at the electrode surface. I'm not telling what is the region. I'm just telling the ions have to come from the electrolyte and form a double layer. So now, when the solution concentration is very small in the sense, here if you see 1 millimolar, it's very small, 0.001 molar. So for such a small value, what happens? It is difficult for the ions to come immediately from the bulk solution and get absorbed on the double layer. Get absorbed on the electrode. I hope you are getting that. The ions are very small in concentration. It is difficult for them to diffuse and come onto the electrode and get deposit to form a double layer. While in case of as high as 1 molar, if I compare it to as high as 1 molar, there are enough ions. So these ions can come fast and they can diffuse and they can form a double layer. So when the ionic concentration is very small, it is not easy for the ions to come from the solution and form a double layer. So if the solution concentration is very small, as small as 1 millimolar, we can go for Gui-Chapman, which says there is a larger region. I mean larger electrode-electrolyte interface as large as 10 nanometer for the charge distribution to happen. But in this case, 1 nanometer is enough. 1 millimolar. But if the concentration is very large, it's easy. The ions can easily diffuse and form the doublet. So if it is very high, 1 molar or more and all, we can go for Helmholtz. Otherwise, we can directly go for the Poole-Chapman model. Is this clear? Is this clear to everyone? In that case, I'll move to the next question. Yeah, who can answer this question? Why is lugging capillary used? So option A, to minimize the solution resistance between the working electrode and the reference electrode. So the next one is to minimize the solution resistance between working electrode and the counter electrode. Third one is minimize the solution resistance between the counter electrode and the reference electrode. Third, the last one is both A and B.
I think C.
Okay.
But okay.
You want to tell
Minimize
something?
resistance between working.
Sorry?
Actually, it is used to minimize the electrolyte
Yeah, D.
resistance.
Okay,
Option D.
Option D. Okay.
The option D. Option D.
Okay, option D. Okay, so that actually, okay, so we know that there are 3 electrodes. In the sense, if you have to measure the potential of one electrode, so you also need, so you have this is the electrode of your interest. You will also use working electrode, so and you will also use counter electrode. So let's see what is the function or the why we are using each of the electrode. Okay. So this is the electrode of my choice. So when I am actually applying a potential across the working electrode. So working electrode, I'm sorry. So, so this is the working electrode. So you all know what is working electrode, the electrode of our choice. So we have a reference electrode and the counter electrode. So we are applying a potential across the working electrode. This is the working electrode. So what is the function of the reference electrode?
To maintain the constant potential.
To maintain the constant potential? Yes. So when it's immersed in solution,
So that we can find the potential.
So that we can find the potential of the working electrode. What is the function of the counter electrode?
To collect the current.
To collect the current.
So that the reference electron won't get affected, ma'am.
Yes, so that the reference electrode don't get affected. So as you told, why do we need to maintain a constant potential across the reference electrode? So that whatever potential when we are changing the solution and we are measuring the potential, the value we are getting is always that drop in the the change in the potential is always associated with our working electrode, right? So always the potential is getting measured between the working electrode and the reference electrode, right? While the current is only passing through the working to counter. So potential is between the working and the reference. So we know where is the potential drop happening. We are applying one potential. So this was also taught
between the working electrode and reference electrode.
Yes, the working and the reference electrode. We know that at the interface in the solution. So actually we should get, when you are applying a potential, we should get something like this, a constant potential. Or I can say E equilibrium, or one potential which I have applied. I am representing it by E or V. But what actually I get is something like this. Why? There is a drop in the potential that is happening across the solution, right? And this is the actual curve you get, this one. So it is not a constant, it will drop and then it will become a constant. So this drop is happening at the electrode-electrode interface. And you know that this potential is measured with respect to the reference electrode. So the role of measuring the potential is between the working electrode and the reference. So the resistance or the potential drop which is occurring is also in the solution. So please tell me now, So where should the solution resistance be minimized?
Option A, ma'am.
Yes, so it should be minimized between the working electrode and reference electrode. Is anyone having any doubt in this? Okay, I hope the concept is clear. So the function of the working electrode, the reference electrode is to measure the potential. Okay, the potential of the working electrode is measured with respect to the reference electrode. So counter electrode's function is to take away whatever current is passing through the working electrode. So working electrode and reference, so basically the potential you apply, you see that potential drop is at the electrode-electrolyte interface because of the solution resistance. So resistance is also offered by the solution. So at the electrode-electrolyte interface and the solution, you will see that drop. So in order to minimize that resistance between the working and the reference electrode, we are using a lugging capillary. So basically there are times when your electrode is, anyone wants to tell something?
Madam, can you repeat what is the function of an counter electrode?
Okay, so I hope you know what is a reference electrode. I mean, function of reference electrode is clear to you. Is it?
Yes.
Okay, so now coming to the counter electrode. You are having a system. This is my working electrode. Okay, and I have a reference electrode and a counter electrode. Okay, so initially if I am going only for a two electrode system in the sense I want to measure a potential, I need only, if I'm of a mindset, I'll go only for working and reference electrode. What happens? You are measuring the potential between both of them. Potential is measured with the rest between both of them. Okay, but when you're applying potential, what happens? There is a current generated, right? So what happens if you're applying a large potential? When you're applying a large potential, similarly, the current you obtain will also increase, right? When potential is increasing, you're getting a large current also. So if in case counter electrode was not there, all this current will pass between the working and the reference. So what is the property of the reference electrode? Reference electrode is something which should maintain a constant potential at the reference electrode is something which should be maintaining that constant potential in whichever solution you drop it, whichever solution you are immersing it, it should maintain the same potential. But when you're passing a large current through it, what happens is it will actually change the property of the reference electrode. In that way, you will not be able to measure the reference, you will not, that constant behavior of reference electrode will not be exhibited. Instead, its potential will keep changing in every solution you immerse. So you will get incorrect reading. So you need something that can pull or take away that excess current from that system. So for that, what is done is a counter electrode is used. So whatever current is going through the working will directly go to the counter electrode. Now, how should be the counter electrode? So working electrode will have a large area. Working electrode, you're applying large potential, you'll get a large. That means a large current is generated. And as I told, all this current will go through the counter electrode. So whenever you are measuring, what you are actually measuring, you are applying current. So all this current goes over here. So what happens? That large current which was applied in working electrode is also going to the counter. But the counter should be able to take up that excess, that large current, right? So so materials like platinum can be used as the counter electrode. Why? Because it is inert. It will not take part in the reaction. Now, another thing that needs to be kept in mind is that it should have a large area, right? When large current comes from working, it should have significantly large area so that the current, okay, current I'm representing by capital A, per unit area, okay, current per unit area is represented by A, becomes small. So when area is large and you have a large current coming, if area is very large, that current which is getting applied per area will reduce compared to if you had a smaller area. So this potential, which is, so what is happening? You are applying a current, the current at the working electrode. You generate a current at the working electrode. That same current will be happening at counter. It is not that the current which is developed here is directly going. What is happening? This current is maintained using a potentiostat equipment. So this current is applied by the potentiostat equipment. So if here the current is large, significantly large current will appear over here. The equipment has to apply that much current. That is not good for the equipment functioning. So instead what we do is it should have a larger area so that the current per unit area that the equipment has to apply or the load will reduce significantly. For that purpose, the counter electrode should have a large area. So basically PT will be used because of its inert nature, and something of the form of mesh will be used. Mesh will be used so that it will offer a large area. I hope it is clear. Any doubts?
Okay, thank you, madam.
Yeah. So,
So
yeah.
one doubt, madam.
Yes.
When we used to do the impedance or a cyclic voltammetry,
Mm.
if the working area is larger than the counter electrode, how you can examine that area is not sufficient?
Area is sufficient in the sense if you are using something like working electrode is 1 cross 1, you can go for slightly larger area, something like 2 cross 1. Basically, it means it should be
Okay.
a little larger area.
No. If the area of is not sufficient, for example, platinum, how you can recognize that working area is larger than counter working electrode area?
Working electrode is fixed by you. You know what its area will be, right? We are
No,
immersed.
yeah, we will fix, but it is supporting or not that platinum mesh. How much we have to use like that?
Okay, so if this one working electrode is of 1 cross 1 area, you can go for something like 2 cross 1. By basically what I'm talking about is the normal rectangular, not the exact measurement. The entire area can be 2 cross 1.
Okay, we can double the area of
Yeah,
the working
something,
electrode.
yeah, not
Yeah,
exactly double, slightly larger, that's all. Might be 1 cross
yeah.
1 means you can go, yeah. So accordingly you can go.
Okay,
Mm.
thank you.
Yeah. Anything else? Doubt? Anyone? Okay. Then in that case, we'll go to the next question. So the next question is, what is a compliance voltage? Uh, so V over here represents the potential, WE is the working electrode, and RE reference electrode, and C is the counter electrode.
It is the voltage between counter and working electrode.
Counter, the working electrode. Anyone else? Anyone else wants to comment? So there are two types of voltage. The one is applied voltage. Okay, one is applied. And the next one is compliance voltage. So applied voltage is nothing but it is the difference between the voltage of the working electrode. Basically what we want, the difference between the working electrode and the reference electrode. So this is the potential of our choice. But as I told you, what I told you, when I'm applying some potential at the working electrode, some amount of current is developed. Okay, and in order to maintain that current, what happens is that equal amount of current will be applied by the potentiostat at the counter electrode. Okay, so in order to maintain, I'm again repeating, in order to maintain some potential, in order to maintain, so when I'm applying a potential at the working electrode, some amount of current is developed. So in order to maintain that same amount of current, what is happening is potentiostat will be applying that particular potential to maintain that same current at the counter electrode. We know that the current is same at the working and the counter. That is how the circuit comes. So what happens is, yeah, so how does that equipment maintain that current? So basically a potential is being applied by the equipment onto that counter to maintain that particular current, right? So compliance voltage is nothing but it is the difference between that working electrode and the counter electrode. So this is the option. Now why is this important? This is very important in the functioning of an equipment, in the sense if anyone is using a potentiostat, you know it will mention already this is the current range it can work, okay, and along with that you can see something called the compliance voltage. So every equipment has a compliance voltage, or this is the maximum difference in the voltage in which you can work. So basically what does that mean? Your that corresponds, so from that value you can understand based on every potential you are applying, you can the working electrode, you can understand how much is the potential you are applying at the counter electrode. So that gives you an insight on how much is the safe working region, or beyond that you are actually abusing the equipment. Okay, so for any system there is a compliance voltage, that is a region where you can make the equipment work. So so that's why I said in order to maintain a current at the counter electrode, it will be applying some sort of voltage. So that is why in order to, so if the compliance voltage is small value, you want to work over a larger region, what you can do is you can increase the counter electrode area, so that the current per unit area of the counter electrode will reduce, and thereby you can bring down the compliance voltage. Okay, I hope that is clear. Anyone has any doubt? Okay.
Ma'am, still I not properly understood.
Okay.
Please repeat.
Yeah, okay. So there is a working electrode, and we know, so there is a working electrode. So now I'm talking only about the working electrode and the counter electrode. So what is happening? You are applying a potential at the working electrode, right? You're applying a potential. So what happens when you apply potential? A current is developing. You'll get some current on the working electrode, right? So
Right.
we know that whatever current is developed or you get on the working electrode, that same amount of current must be generated or maintained at the counter electrode to complete the circuit, right? We told that the current should not pass through the reference electrode. It is passing to the counter electrode. But what does it passing to counter electrode mean? It's not exactly passing. Instead, in order to, so what is the current over here? The same amount of current will be will be maintained on the counter electrode by the equipment. Are you getting that point? The
Yes.
will be maintained by the counter electrode. So how is the current maintained? You are applying a potential. That is when the current is maintained, right? You apply a potential, you get current. So here this potential is maintained by the potentiostat. So here it is a potentiostat which will be, so here we are applying a potential is applied of our choice. This potential is of our choice. Our working electrode, I want to have this much current, so I am applying this much voltage. So this is my working electrode. But what is the potential which is applied by the equipment on the counter electrode? That is not our choice. In order to maintain this particular current on the working electrode, how much is that same current needs to be maintained in the counter electrode, and to maintain that you need a potential applied. That potential is applied by the potentiostat. So that keeps changing based on the current which is generated over here. I hope you get that. Is that clear?
Yes.
So that particular current, or you need to maintain that current on the counter electrode, that current is maintained by a potentiostat by applying a potential. So based on any change over here, here also that potential is keeping on changing. So there is a difference between this potential which we apply, this is we are applying. Working electrode potential is always applied by us. This is the working electrode potential. But this is applied by us. This is of our choice. This is of our choice. Our choice. This is by our choice. But when it comes to here, the potential at the counter electrode, that is supplied by the potentiostat. Okay, and that is not of our choice, that based on the reaction happening, it is maintained by the potentiostat, which keeps changing. So we know that any potentiostat has a limit on how much is the potential which an equipment working electrode potential, which or the range of potential in which we can measure. That changes from equipment to equipment. That is the only thing sometimes we look. But something else we have to look into is the compliance voltage, because it's not just the working electrode potential that is important, but also to check into how much potential is applied by the potentiostat to maintain the current on the counter electrode, which is also having a limit. So that limit is indirectly given in the form of difference, which is as working electrode potential minus the counter electrode potential. So that is known as the compliance voltage. Okay. Now, yeah. Now the next question. Who can answer? How is the reaction rate controlled when a small potential is applied at the electrode-electrolyte interface?
Kinetic control, no? Kinetics control.
Okay. Anyone else wants to answer?
Ma'am, B.
Kinetics control. Okay. Okay. So yeah. So the correct answer is kinetics control. So if and for everyone's query, I will just explain that question. So two of them have answered. So how is it happening? So I told when potential is applied, whenever I'm applying a potential, okay, I'm giving a graph. So there will be a current. Okay. So how is this graph? So you have something. So when I start to increase the potential, after some times it becomes like this. So sorry. So I'm applying a potential. First, the current increases linearly. After that, will again increase slightly exponentially. After which it becomes not exponentially, it keeps on increasing, and then again it becomes somewhat stable. After which there is a rapid increase in the current with potential. So this is how a current versus potential graph is given. So of which you know there are different regions. In the initial region, I and V are linear. Okay. The next, so here you see whichever potential you are applying, it's a stable value of current. That means there is no much change in the current when you are applying. So this region is known as the mass transfer limited region. Okay, or the mass transfer controlled region. Okay, this region where you see a linear behavior as I is potential is increasing, you see that the current is also increasing. So this is called the kinetic controlled region. Okay. You have the kinetics and the mass transfer. And this region is known as the mixed region. It's a mixed region where both kinetics and the mass transfer comes to play. So now what is happening? What is reaction? How is the reaction rate controlled when a small potential is applied? So you are applying a potential, okay, and because of that potential, what is happening? A reaction is happening, right? You are actually driving a reaction when you are applying a potential. At the electrode-electrolyte interface, this reaction is taking place. So now this potential can be any value. Now what happens when the potential value is small? So basically when you are applying a potential, you are forcing a reaction to happen at the surface. What if the potential, as mentioned in the question, if the potential is very small? potential is very small means, this means that the reaction rate is very small. You need something to be driven very fast, you need to apply that much input. So here small potential means here it is a slow reaction, small reaction, slow reaction that's happening. Slow, or what I mean, it's a small reaction, slow reaction happening. So when you are forcing a reaction to happen, what is happening? You know, the electrolyte will have the ions in it. Some things have to diffuse from the bulk and they have to come to the surface, right? Only then the reaction will happen. Now when the reaction is very small, what is happening? Only small amount of some ions need to come to the surface from the bulk. So if the concentration of the ions that are needed to come to the bulk are very small, that means you have enough reactants in the solution. It's easy for the reactants to diffuse from the bulk to the electrode-electrolyte interface. On the contrary, if the reaction is very fast, means I'm applying a very large potential. Large potential means you are forcing a very fast reaction to happen. So in that case, you need continuously the ions to diffuse from the solution onto the electrode-electrolyte interface. Okay, so that are the two scenarios. So if the reaction is very slow, I mean I'm having enough ions in the solution to diffuse, come to the surface, and the reaction happens. On the contrary, if it is very fast, very large potential applied, very fast reaction, means ions have to come. Sometimes a point is reached when there is no enough ions to diffuse from the solution and come to the electrode-electrolyte interface. So in that scenario, when there is no ions to diffuse, so basically it is then the reaction gets dependent upon the diffusion of the ions. Okay, so that are the two cases. So in the first case, it is basically you have enough ions and it's easy for the reactions to happen, and you say it is kinetics control. So there in that particular region, you see that the reaction is happening smoothly and you have reaction is happening smoothly, and you have as potential increases, you can see that the current is also increasing. So that is the first region. Then you have a mixed region, and as I told, in the mass transfer limited region, what happens is the reaction is very large potential is applied, and when you apply large potential, you see that with the increase, you see the ions are diffusing, and there is no enough ions to diffuse. That finally the reaction is mass transfer limited or diffusion limited. In that case, you say it is mass transfer control. Any doubt for anyone? Okay, if it is clear to everyone, we will move to the next question. Who can answer this? When a sine wave is applied in inductor, options, current and potential are in phase.
Current
Okay, tell me.
current lags, ma'am.
Current lags.
Current
Okay.
lags the potential by 90 degree.
Okay. Anyone else
Yes.
want? Okay.
C.
See, current lags the potential. Okay. So current is lagging the potential. So you should also know what will happen if it is a capacitor, or okay, so you should know how it behaves. So you know how it is in resistor, how it is in capacitor, how is it in inductor. So how are you saying that? So for an inductor, you know that E. So obviously it is an AC current, right? AC current, you have EAC equal to L di by dt. Anyone has any doubt? Okay, you
No,
know,
ma'am.
okay, you know E is equal to L di by dt, and you know I is nothing but it is IAC naught sine omega t. So basically, if I am substituting it and I am differentiating it, so this is I. You know I is equal to IAC naught sine omega t. I am differentiating it. What will I get? IAC naught is a constant. I can take it out. Okay, and you have differentiation of sine omega t, which is not nothing but omega into cos omega t, right? You have omega into cos omega t. Okay, now you already know that EAC can be represented as, how do I represent EAC naught? So this is the wave which I am applying. Okay, I am representing it as EAC naught sine omega t. Okay, now I'm just trying to, I'm sorry, really sorry, just wait. What I meant is, so we are finding out the equation for EAC, that's the potential. So we already know that IAC is nothing but this IAC naught sine omega t, right? So here I have expressed I in terms of sine wave. So in order to compare, I need to even represent EAC, the potential, in the same form. Only then I can tell, right, if current and potential, how are they leading or lagging. So basically, if here also it is sine omega t, here this should also be changed to sine. So you would have learned already to how you can represent it. L IAC naught omega sine omega t plus pi by 2, right? Sine cos omega t is nothing but sine omega t plus pi by 2. So what that means is, if I am applying, okay, if I am applying current of IAC naught sine omega t, the potential that is developed, which is something like EAC. So this can be written as EAC naught sine omega t plus pi by 2. So here the potential is getting it's leading current by 90 degree, right? Here sine omega t, so here it is sine omega t plus pi by 2. So it is in fact the potential which is leading the current, or as you told, current is lagging the potential, and option C is the right answer. Any doubt for anyone? If not, then we'll move on to the next question. I hope this is clear to you. So similar kind of question is there in the assignment. So where it is asked for conductor. So this is how you have to do. So you know the formula, right? Then you will know one of it. If so, based on what it is there's a different formula for capacitor. So what comes over here, you can substitute for that. Can be either E or I, depending on how the equation is. Find out, then compare both. So which one is sine omega t, the other one will be sine omega t plus pi by 2, or what it is, and based on that you compare, and then you will get the answer. So this is one of the kind of question which is there in your assignment. So now the next question. Nyquist plot is, which one is the Nyquist plot? So the first one I have written is minus z imaginary versus z real. The next one I have written minus of phase versus frequency, modulus of frequency, z imaginary and real versus frequency. Who can tell?
correct answer is
Well,
A.
option A.
Minus Z
First
imaginary
question.
versus Z real.
So,
It is between the Z imaginary and Z real, ma'am.
okay, good. So,
Option A.
yeah, option. So, the answer for this question is minus Z imaginary versus Z real. So, basically, in impedance, what we are doing is we are applying a frequency. So, frequency range can vary. So, like if I give you an example, it can be like 100 kilohertz. Okay, it can be more than 100 kilohertz. There are also equipments for that. So 100 kilohertz, something if I say to zero point 0.1 hertz, high frequency region, zero point 0.1 or even 0.01 hertz are there, or even lower. So it depends upon the equipment, the equipment quality, or what range you want to measure. It all depends upon the frequency range you are measuring. So in this frequency range, you are applying a sinusoidal wave, and it will have an amplitude of something like 5 millivolt. So as it can be as low as 5 millivolt, and sometimes you apply 10, you apply 20, and you can also go up to 50. It all depends upon what, or it can be even more. So it all depends upon what feature you are trying to learn. Okay, based on the what feature you're trying to learn, you're trying to do. So when you're applying a frequency, you will get a plot, and this plot, either it can be minus Z imaginary versus Z real, the impedance part. So that one you call it as Nyquist plot, or it has another name, which is complex plane.
Complex plane plot.
It is complex plane plot. Good. So it is complex plane plot. Now, what are the other three known as?
Bode plot.
Body plot. So some people are interested to know how the magnitude or how the phase is changing when it's changing the condition, etc. So some also go for the body plot. So all these three are body plot. So this is the body plot. Now,
And why here negative Z impedance is taken?
that is a representation. So you will sometimes encounter negative values of imaginary part. So that is why you are doing. That's how we represent. Why exactly means when you're solving, you will get that. So we are using it. There isn't a particular answer for that. This is how whatever you get might be in a negative value. So that is converted into negative. So basically your imaginary part in many problems can be negative. So in that case, you take a negative of that value and plot so that it comes to the positive axis. That is how it is.
Ma'am,
Yes, then.
ma'am, option D is a 3D plot.
Yeah, but that also comes under, that is also body only.
Okay, ma'am.
Yeah, that was how it was told. That's also body. Okay. Oh, sorry. I'm sorry. These two are body, or you can say that as 3D itself. Okay. I'm sorry. Uh, so these two are body. Okay. Then I'll write like that. So these two as body. Okay. And this one as a 3D. Okay. Now coming to the next question. Anyone has any doubt?
Actually, ma'am, the minus sign that has been given is due to the mathematical notation of the imaginary part. Because whenever we used to draw imaginary axis,
Hmm.
I think that we used to denote it by minus I.
Yeah.
So that is why that is minus Z imaginary is that minus is to denote the imaginary part of the
No.
impedance plot that we used to plot.
No. The negative is actually to take the negative of the value of t. I'll anyway
Okay.
confirm it in the next class to you again. But
Okay, ma'am.
I'll just write it down. Uh, Yeah, so basically, when you are doing the impedance, you may encounter the negative value. So that as per my knowledge, in order to bring it to the positive axis, we are using a negative z imaginary. However, I'll again clarify this and confirm with you. Okay, for the next class.
Maybe it is converted from fourth quadrant to first quadrant, so
Yeah, that's what
negative
I.
is converted into that
Ah,
may happen.
yeah, that is what I am telling
Fourth to
you.
first quadrant.
But however, I'll confirm once again because you have a doubt. So, as per my knowledge, when you are doing impedance, your imaginary part can be negative. So, when you're plotting it, you don't want it to go to the negative axis. Instead, you want everything in positive axis. That is why you are using negative. I'll again confirm and let you know in the next class. Okay. Now going to the next question. This is a problem. Everyone can try this out. I'll give you 5 minutes. What I want is the expression of the form a plus ib. Z, I'll just, I want it of the form. So these questions I'm not giving any options. You can write it and you can discuss your final answer. So what I actually want is, I want something of the form this. Z real plus J into Z imaginary. So I can give you 5 minutes. If anyone gets the answer before that, you can let me know. Okay. Yeah. If anyone has a doubt on how to do, please you can ask me so that I can give you some hints.
Ma'am,
Hmm.
as they are in parallel, I have to first find the admittance and I have to find the inverse of it to find the impedance, right?
Yeah.
Then I can directly add R1 and the net impedance
Yeah.
from this.
Correct. So if anyone has any doubt on like how to proceed, I'll just again say what the student has told now. The idea is you can so you know this in parallel, you can find the impedance of this system. So how you can find the impedance of this system? Either you can find the impedance of capacitor and impedance of the resistor. So we know it is in parallel means for a parallel connection, impedance will be nothing but inverse of the impedance will be the sum of the inverse of the individual ones. That is 1 by Z will be nothing but 1 by impedance due to capacitor plus 1 by impedance due to resistor. Like that you can find out the impedance of the system and add it to this. Or another way to approach is, when you know it is parallel, you in terms of admittance, you can say that the net admittance of this parallel system is the series sum of admittance of capacitor plus the admittance of the resistor. You can then add them, then you can take the inverse of the net admittance to find the impedance of the system and add it to the impedance of R1. Anyway, that's up to you. You can either follow the impedance method or you can follow the admittance method.
So, ma'am, answer is 220 minus J 530.78.
Okay, I'll write down everything. If any, can you tell me once again?
220
Hmm.
minus
Hmm.
J 530.78.
Hmm. Okay. Okay. Someone else has some other answer? I thought I'll write down all the answers and then discuss. I'll wait anyway for 2 more minutes. Anyone else has answer? I'll let you start.
I'm working out now.
Huh? I didn't get
I'm
you.
working now.
Okay, I'll give you. Okay, do I need to wait? Okay, I'll give you.
Still solving one.
Yeah, sure, sure. I'll wait for 1 more minute. That's fine. Uh, shall I continue?
Yes, ma'am.
Okay. Do you have an answer or?
I'm still working. Ma'am, if
Okay.
I'm having an imaginary part in the denominator, I have to multiply it with the. I have to change the
Complementary.
symbol so that
Yeah. If
it
you
will
have.
be a squared minus b squared formula.
Yes, yes, that one only.
Okay.
Yeah. So, okay. So how do I approach this problem? What do I do is, I will not put numbers in the sense, I'll first solve it and I'll get a general expression and then I'll substitute. Why do I do that? Because now if you see you have 30 microfarad, 30 into 10 to the power minus 6. If I keep doing it, somewhere or the other I can make a mistake. So how to avoid that? I'll just use ZR1, ZR2, ZC1 and I'll do it. And finally I'll get a simplified form and then I'll substitute. That's how I proceed for this question. Okay. So first I'll be dealing with the parallel section, the parallel section. which has a capacitor in parallel with the resistor, and the form I like to use is the impedance. Okay, that is how I prefer doing. So I told anyone can go with impedance also. So you know 1 by Z parallel will be nothing but it will be the sum of the parallel of ZC1 plus 1 by R2. Imagine 1 by R2. Okay. So if I am taking the inverse, what does that mean? ZP is nothing but it will be 1 by, I am just taking the same thing again down, 1 by Z, okay, 1 by ZC1. What is the impedance due to ZC1? What is ZC1? The impedance due to this is nothing but
C omega J.
okay. Is it C omega J or 1 by JC omega? 1 by
1 by
yes, don't get confused.
1 by J.
So it is 1 by JC1 omega. Okay. So if I'm substituting it over here, you can see it is 1 by the entire thing, right? This entire thing, so I've just taken the reciprocal, this entire thing should come over here. So I'll just first write down 1 by ZC1 plus 1 by ZR2. And we know 1 by ZC1 is nothing but, as told, it is JC1 omega.
C.
Okay. Plus, could you please
1 by
make
R1.
1 by R1. 1 by R1, no, 1 by R2. Be careful.
R2.
This
R2.
R2.
Yes.
1 by R2. Now I want to make it into a simplified form. So I'm cross multiplying with R2. So what will happen is R2 will go up. Okay, and you will have J C1 omega R2 plus 1. So this format you got. Now we know, so I'm having J in the denominator. So how to get rid of that? So it is something of the form A plus IB. So we know A plus B into A minus B is A square plus B square, right? Same thing I am doing. I will apply a complementary. Okay, that will be A minus IB. Okay. So I'll get nothing but A square minus I into B the whole square. So we know that I square is nothing but it is equal to minus 1.
Minus 1.
So this will be nothing but A square plus
A square plus B square.
B square. So this is how the same formula, I mean complementary, I am applying over here. Okay, I am doing it over here. So I'll get Z parallel as nothing but I have R2. So I'll take it as 1 plus JC1 omega R2. So I am multiplying by 1 minus JC1 omega R2. Okay. And downstairs what I'll get is 1 plus C1 omega R2, the whole square. Is this much clear to everyone?
Yes, ma'am.
Yes. Now, so this is the Z total. So I told you I need it in the form of Z real and Z imaginary. Okay. So what is Z real? It will have everything except the, okay, sorry. So this is the Z parallel. So now what is Z total? So I'm writing total in the form of ZT, denoting the total, which will be nothing but, so this entire thing is in series with this one. So it will be nothing but R1
R1 plus ZP.
plus ZP. Okay. So always simplify this in this form. Why I tell you is, if you substitute all the values at the starting itself, then you will get confused, because you will have a 10 to the power minus 6 at the numerator and the denominator, everything, and you have a square, everything, it will become mixed up. So best thing is always simplify it, and then, because the problems are small, it is very easy to do. So if you get the form, then it's easy. So now you know the real part is nothing but, I'm writing Z real as, you'll have, so this one R1 is having only real part, so that will have come as R1 plus, you see it is R2 into 1 minus JC1 omega R2, where only into 1 is what you can take, R1, because the other one is for the imaginary, R1 by, same thing, denominator 1 plus C1 omega R2, the whole square. Okay, so this one is the first one, the real part and the imaginary part. So imaginary will be nothing but, it will be don't forget the minus R2 C1 omega, and you have another R2, so R2 square by same denominator. Same thing will come in the denominator, 1 plus C1 omega R2, the whole square. Now who can substitute the value and tell me the values of Z imaginary and Z real?
Ma'am, in Z real formula R1 plus R2 divided by.
Ah yes, R2. Who can tell the values? Okay, I can show you the answers, I mean questions again. I can give it 2 more minutes, just substitute and find out the Z imaginary and Z real part. Has anyone got the answer?
Z real is 195.11, ma'am.
Okay. And your imaginary?
That is, I'm getting it in negative value, ma'am.
Yeah, tell me.
Minus 0.33.
Minus 0.33. Anyone is getting
Yes,
a
ma'am.
different answer? Uh, because this part is same as my answer. This one I'm getting slightly different value. I'll also once recheck it. Okay. Because I'm getting around 6.5, minus 6.5.
Ma'am, wait a second, I will redo it. I'm having a calculator.
So it is R2 square, which is nothing but 200 square, and you multiply that with C1. C1 is something which is 30 microfarad.
I'm getting the same value again, ma'am.
Okay, 0.33. Okay, just wait. I'll
Yes,
also
ma'am.
confirm.
Yes, ma'am.
Hmm. Hmm. Um, So at the denominator it is 200 square into 30 into 10 to the power minus 6, right? 200 square into two, 3 into 10 to the power minus 5 and 62.836. Hmm. I'm still getting a slightly different value. Okay. It's okay. Like, okay, if you're getting this value, if you're sure with that, let's move on with this. Okay. I'm not sure because I'm getting some value around 6. Okay. So this part is different, which I'm not sure why I'm getting a different value. Okay.
Ma'am, can I tell the formula again? Maybe
Yeah.
I would have written the formula wrong. It is
So,
minus R2 omega C divided by
no, minus R2 square.
squared. Okay, that's why I got wrong,
Aha,
ma'am.
okay.
If
Okay,
I'm
just,
multiplying the answer with R, I will
okay.
R2,
Okay.
I will get the value. It is
Okay, okay.
66.
Yeah, yeah. Now I'm getting
Now it
correctly.
is right, ma'am.
Yeah, it is 66
Okay,
point.
ma'am.
Okay, I was getting 66.9. Okay, correct. So I was getting around
Okay.
66.9. So yeah. So I have corrected here. So this is the value for the impedance. I hope it is clear to everyone. So this is the real part and this is the imaginary part. So now the next part of this question. What is the magnitude of the impedance for the following circuit?
It is the same problem.
No. Now the question is to find out Z, modulus of Z. What I first asked you is to find out the
Oh, okay, ma'am.
impedance.
Okay.
Now you find out the modulus. I'll also do meanwhile.
Ma'am, will it be the square? I
Hmm.
have to square it and I have to,
Yeah.
and then I have to take the root of it, right, ma'am?
Yes. So
Two
it
Uh,
zero
will be
okay.
206.26.
okay.
Yes, ma'am.
Okay, correct. So it is nothing
I'm
but
also getting the value.
So it is nothing but it is square root of z real square plus z imaginary square. Okay, and we know the value of z real is around 195, and the value of z imaginary is around 66.
66.
Yeah, 66, 67 you can take.
So we will get
Yeah, and then you will do the square root of this. Okay, and if you do, you will get around 206. 206 to 207 range you are getting the value. This is the magnitude. Now the next question is, okay, I hope that is clear to everyone. Okay, now the next
yes,
question
ma'am.
is to find out the phase. Same question, phase.
Then what's the formula, ma'am?
Okay, sorry. So so once you find out the impedance equation, you need to find out the magnitude, which is given by modulus of the modulus of, is real the root of z real square plus z imaginary square, and the phase. Okay, the phi value is given by tan.
Tangent inverse of
Yeah,
x upon y.
yeah. Sorry, y upon x.
Okay.
The
Okay.
Be careful. It is nothing but the z imaginary part versus z real.
Ma'am, the answer is 0.33.
0.33, is it? Please check once
Uh,
again.
0.0059.
Okay, okay. Please find the answer in degrees.
Okay.
Degrees, okay.
Yeah, because we say that current is lagging this by this much 90 degree. Find it in, yeah, what you would have told 0.33 is in radians, right?
Yes, ma'am.
Yeah, so always,
In degrees, it will be 18.9.
okay. Is it only 18.9?
18.935.
Not that. Something else you're missing? Minus, yes. Minus is important
Yes. Yes.
because if you go back, you have this 195.11 minus J of 66.9. So this is the real part, and this minus comes along with the imaginary. Okay, so don't forget this minus when you get the questions. Okay, that's a very like frequent mistake because of which you will lose mark. So always don't forget to take that minus. It is nothing but minus 18.9 degree. So this is the answer. Now, yeah. Um, Now I'll just because we'll wind up in another 15 minutes. We'll discuss some questions which are important from the assignment point of view. The rest we'll do in the next class. Okay. Yeah. So what is the impedance for the following circuit at low frequency? So question of this kind has been given in the assignment. You can take few minutes to familiarize with the question and then we can solve it.
It will be R1 plus R2.
Okay. Someone is saying R1 plus R2. Anyone else has any other answer?
Yes.
Yes, what is it?
R1 plus R2.
R1 plus R2, okay.
But at low frequency,
Okay, madam. R1 plus R2. If it is a capacitor, it is an inductor.
It is R1.
It's only R1.
No. It is R1 plus R2. R1.
Okay.
Yeah, it is R1 plus R2.
Okay. For everyone who is saying it is R1 plus R2, can anyone explain why it is so?
The current won't be able to flow through inductor. Hence it blocks.
Sorry, I didn't get you.
The current won't be able to flow through the inductor, ma'am.
Why?
Because
I think
the resistance will be, impedance will be very high. Impedance will be very high.
Why is impedance very high at low frequency for inductor?
No, ma'am. No, here
so it is
it will be R1.
R1, okay.
Yes, ma'am.
Okay.
Because it is directly proportional to.
Okay. Okay. And now I'll
Okay,
tell
ma'am.
you
The impedance of the inductor is directly proportional to the frequency, ma'am.
mm,
Hence, at high frequency, um, the current won't. It will be acting as a short circuit, so that it is only R1.
okay. Okay. Now I'll explain. So what is happening? When I'm passing a current, okay, when I'm passing a current, it will pass through the resistor. Uh, uh, can someone mute? So much noise is coming. Okay. So this question is very important because you have such a question in the assignment. Okay. So only difference is there it is capacitor, here it is inductor, right? So so how to approach this question? What is happening? You have a resistance resistor and One here, inductor and resistance are in parallel. So what is happening? I am passing a current, it reaches here, okay, and over reaching here, it can go either through this way or it can go through this way, right? Can go on either way. So which way will it choose? So here now I am saying it is for a low frequency. So first you should understand what are the resistances. So ZR1, anyway it will pass, right? Impedance of R1 is nothing but it is R1, right? Now impedance of ZR2 is R2. This both you know. Current or potential will anyway pass through R1. Now which path will it take? Will it go this way or this way at low frequency? So the answer lies in impedance of the inductor. What is the impedance of the inductor? It is nothing but it is
J omega L.
Yes, J omega L1. Now, when current is reaching here, now it depends on, so obviously, when you have many circuit, what happens is current will pass through the easiest one, through which it can go very easily, it will go through that. That is how it works. Okay, so if you see at low frequency, so here what all, these two are in parallel. Now the question is which one will it pass through? So if I am taking, I will first look at the inductor. So for a very low frequency, what happens? Omega will be very small. So case where omega is becoming very small. So as omega is becoming small, or I can say omega tends to 0. So basically at low frequency means omega tends to 0. That's just a notation. What is happening? ZL.
It's a short circuit.
Yes. ZL will keep decreasing. So it keeps on decreasing. So what happens? Which path is easy to pass through? Is it
Inductor.
Inductor.
Inductor. Why? See, what I am saying is this way it is having very less resistance. R2 is there. R2 has its own resistance. It has no effect of frequency. Whatever frequency it is, R2 is fixed R2. On the contrary, what is happening to L1? L1 keeps on decreasing. I mean, the impedance of the inductor is keeping on reducing when the frequency is reducing. So what happens? The current will pass through this way. Okay, this is the way through which current will pass. The current will go like this, it will go like this, and then it will go out. I mean, it will not go in this way. So if I reduce this, it becomes nothing but I have R1 which is in series to the inductor. Now anyone can tell me what is the impedance?
R1.
R1. Is it only R1?
Plus J omega L.
J omega L.
Yes, don't forget that. Why? This entire path is offering resistance. It is not just R1. It passes through R1 and goes through an inductor which is also offering a resistance, which is nothing but J omega L1. Don't forget that. So basically when such a question comes, what you have to do is you have to decide which path it is going through. Okay, the other path you will cut off. Then it becomes a series combination. Then you have to just add the impedance of whatever symbols are there. Okay, so that is how you find out the
Ma'am, but
How do we ensure it is
ma'am, but
lower
J
than R2?
I didn't get it. One by
but
one.
J omega L is very low, right, ma'am?
Yeah, that is the point.
J omega L value is very low.
Yes, that value is very small.
So it's
so
more or less R1.
but you cannot take the exact. See, frequency tends
Okay.
is a small, low frequency. That is all what I told. I didn't say it is very small. Still, frequency will be having a value, right?
Okay.
In such question, either see, what if it is something like 0.1 or something? What it means is at low frequency, which so it is basically I am asking you how will you reduce the circuit. What is tested over here is your analysis to understand whether the current will pass through L1 or R2. Okay, so from question point of view, you cannot neglect it. Still, it is offering some resistance, right? You cannot neglect a resistance. So yeah, the point of view of this question is to understand through which way it is passing through.
Madam, but in
Okay.
such case, we cannot neglect if R2 is lower than that J omega L, then we
See,
cannot neglect current passage through R2 also.
no, you cannot. But usually, from the question point of view, I mean, for problem point of view, this will be something around 10 or
Just
20.
this.
Yeah. See, this is from the questionnaire point of view. When such question comes, might be the values over here, you have something like 10 ohms. Or, and here if the question is at 0.1 omega and it is only having some, this is having something value where you add up, I mean, when you multiply, you get some value lower than R2 resistance. So obviously it will pass through this, right? Resistance is having its own value. So this basically from a questionnaire point of view, how can you, simplify a impedance data, what to say, circuit to find out the resistance. Okay. I hope that's clear. In reality, it still depends upon, as you told, if the resistor value is small, then it is obviously going to pass through the resistor. But this based on the theoretically, if I'm saying, if I'm giving you some calculation point of view to find out how much is the total resistance at low frequency, what is the actual point of this question is, you need not have to sit and solve like this. So presently, if such a whole question is given, what will you do? You'll have to solve. You have to take the parallel connection. You have to find out the value. Then you'll find out the real part and the imaginary part, right? So that is how the actual. Then you will find out the total impedance. No, if the question has already mentioned to you that it is at a low frequency, you need not have to do the entire step. So basically, it is like another way of asking a question where instead of, so this based, I told you this from the questionnaire point of view. If in the question you are given this figure and asked to find out the impedance, you need not have to do this. In case if it is mentioned high frequency or low frequency, all these steps are not needed. What you have to directly do is you have to apply this condition. You have to see whether it's inductor, capacitor, simplify it and find out the impedance. So basically it is saving the time. This is the answer that the person who is trying to analyze you trying to find out. Okay. One more question of this kind. At high frequency, how will it be? Anyone can tell?
It can work as a open circuit,
R1 plus
R1 plus R2.
R1 plus R2.
Yeah, correct. So you know that here it is j omega L, and that means at large frequency this impedance will be very high. So this one will be an open circuit. So current will obviously go through the path which is easy for it, and it will choose this path, and here it will be R1 in series with R2. Okay. And so basically when such question comes for your exam or assignment, they would have given the value of what is R1, what is R2, what is L1, and you're supposed to find it. So here I have not assigned any value. So what it means is you have to just substitute it and find out the value in actual question. Now, other type of question. So whatever you're learning now is not just for your assignment point of view, but also for your final exam if you are all registered. So another possibility
Ma'am,
of
in assignments, how can we write the answer? In
assignment.
assignments, how can we write the J, ma'am? A J value, because if I'm writing the R1 value, for example, for R1 value is 200, if I'm writing 200 plus, put that symbol in the assignment, ma'am. Plus J, I can't put that.
Is it? Can you do one thing? Okay. Can you do one thing? Can you post this question in the discussion? So discussion poll. I'll reply to you there because I have not checked that.
Okay, ma'am.
You know how to post the question in discussion? Okay. Just you have to log in. Okay. You have to log in,
Okay.
and then you have to go to the course. At the top, could you tell me which is this question number where you're not able to type J?
No, we can write, Abhi, we can write only the value of J. So in the question, it's asking imaginary.
Okay, 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 okay.
So we have to write the negative value or positive value of the imaginary part.
Okay, okay. Thank you.
Okay, if that is clear, then that's okay. If any one of you, because I have not checked the assignment, if any one of you has any doubt related to the assignment or anything, please post your question in the discussion poll. Basically, you have to log in, and when you log in, you have at the top itself many options, assignments, and side you can see discussion poll also. Discussion. So there you can go and you can post your question directly. So where I will itself be answering it. So because I have not checked the assignment questions, I am not sure of that. If your question is still not clear, please post it there. I will reply to you in one day. Okay. So that is like that. So now coming to another few suggestions. So now here, if you see, this has been done from like how to simplify and find. So here instead of capacitor, you can also have a inductor. So in that case, the only difference will be ZL will be J omega L. J omega L. So here instead of typing J omega C, it will be 1 by J omega L, and you'll continue. Same way you'll get one Z real, Z imaginary part, substitute and find out. Okay, that is another possible question. If it might not have come for your assignment, but might be for your future final exam, this question can again come. So follow that methodology where you're simplifying it and then substituting the value, because if you substitute at the starting itself, it can become completely messy because of microfarad and all. So that is why I'm telling you, substitute at the end. First simplify it and find Z real, Z imaginary, then substitute. Then the next thing to keep in mind is don't forget the negative symbol. Okay, here when you come here, imaginary might have a negative part, use it. Then apart from that, you should know the different type of model. You should know why reference electrode is used, why counter electrode is used, why the area of counter electrode should be large. Then you should know how is the in capacitor inductor, how current and potential is leading or lagging. Should know how to find admittance, how to find impedance. And finally, yeah, PDP, OCP, CV, the scan rate, what is the difference, etc. Then you should know what is body plot and Nyquist plot. So these are the topics that were covered. So this was another question that I thought of discussing, but since the time has exceeded, I'll stop. So as I told, it is same as the last question which I said. The only difference here, it is inductor, substitute it and find it out. Okay. Now, if you had gone through week 1 lecture, you would have seen the tutorial part where sir is discussing about the graphical representation. See, that is another a wonderful part of the impedance. So if you all are having MATLAB, you can just try that out, so that from next class, if time permits, we can also discuss that. Again, obviously, those questions won't be from the you cannot expect such questions for your NPTEL exam, because you will not be, basically it is 1 mark, or you will have MCQ or 1 word, such kind of question. Basically the other one which sir has discussed is about MATLAB coding, and but that is a wonderful part. So whatever
But
tell
we
me.
need to understand that. That was
Yes,
the
yes.
interesting part.
Yeah, that is the interesting part. That was what I
Yes.
was telling. So if all of you are interested and you guys have MATLAB, I'm planning to show that in the next class. So if you are all interested, do join. And if you have MATLAB, please bring get that
Please.
also ready. So then that becomes more interesting. Rather than just studying the theoretical aspect, please try to learn the actual aspect. So basically, all this can be plotted. You have its own form. So when you are plotting, you'll get a shape. It is from that you can actually decipher a lot. So that is the actual meaning of EIS. So if you all are ready, I'll show that in the next class. And I also request you guys, if you have access to MATLAB, take that also. So meanwhile, when I'm coding, you can also try that out, right? So that will make you also learn a lot of things. Okay, so that's all for today's class. Thank you everyone for
Thank you.
joining. So I'll be joining like this every Tuesday, 7 to 9. All who are interested, do join. We can learn a lot together. Thank you everyone.
Thank you so much, Cyril. Thank you so
Thank you.
much.
Thank you.
Thank you so much,
Thank you.
ma'am.
It was very
Thank you.
interesting.
Thank you.